Now, so far, we were talking about ideal fluids. Now we're going to change that up a little bit. We're going to talk about fluids that have some viscosity. A laminar flow is a fluid flow that we characterize by the smooth flow of fluid in layers that do not mix. Those are the laminar flows that I was showing you over the airplane in one of the earlier videos. Turbulent flow or turbulence is characterized by eddies and swirls that mix layers of fluids together. So we have turbulence when those fluid parcels have some angular velocity around a central point. Viscosity is the description of how easy or difficult it is for a fluid to flow. And here is how viscosity is defined. We use the Greek letter eta right here. It looks kind of like a fancy N, and it equals a force times some characteristic length, we'll call it, that's the big L, divided by a speed of the flow times some cross-sectional area. So we're gonna use that definition and think about it in this figure over here. Okay, so the viscosity of a fluid can be determined experimentally by finding the force required to move a plate at a constant velocity some height above the bottom of the fluid. The viscosity always has to be determined experimentally. It's a property of that fluid. For example, syrup is viscous, water is not. Honey is viscous, water is not. Tar is viscous, water is not. Pressure differences can also cause fluid flows, and this we find to happen a lot inside the interiors of stars and planets. Pressure differences between two places can cause a flow of material, a flow of fluid, a flow of gas in the planet's atmosphere. Actually, it happens in our Earth's atmosphere too. A pressure difference between 2 points on the planet can cause a flow of wind. It can cause weather patterns. Okay, so a change in pressure between 2 points in a fluid can cause the fluid to flow. The greater the pressure difference between the 2 points, the greater the flow rate. And here is an equation for the flow rate of a viscous fluid, okay, a fluid that has some viscosity. So the flow rate is equal to the difference in pressure between 2 points divided by this quantity R here, which is what we're calling the resistance to laminar flow. And that resistance to laminar flow is defined by the viscosity of the fluid, the length of the, let's say, tube through which that fluid is moving, divided by pi times the radius of that tube to the power of 4. So we'll say that this is the flow rate inside a viscous fluid that's moving through a tube in this particular quantity here, okay? So the flow rate is the change in volume per time. We can write that as the difference in pressure over our resistance to laminar flow. And so then we've got the difference in pressure times, R here, 1 over R would be the inverse of what we're seeing right here. So then we multiply the difference in pressure by the inverse of this quantity that we're calling the resistance to laminar flow. And that's right here. So the flow rate of a fluid is dependent on so the flow rate of a viscous fluid is dependent on a change in pressure between 2 points and some quantities that have to do with how viscous it is and what sort of geometry are you moving that fluid through. So over here we have some examples of the difference between a viscous fluid and a non-viscous fluid and how they behave when they move through a tube. So here's an example of an ideal fluid that is not viscous. And we've got a tube here, and we see that the fluid moves at the same speed wherever you are inside the tube. But if we have a viscous fluid over here, viscous fluids inside a tube Viscous fluids have zero velocity near the walls, and they reach their maximum velocity at their furthest point from the walls, which would be inside this fluid right here. And this flow rate inside the tube through which this viscous fluid is moving is dependent on the change in pressure between one end of the tube and the other. We're going to use this idea in order to solve a problem related to the medical profession and relating to blood.
We're going to apply flow rates in viscous fluids to a problem where we think about a blood transfusion, so a medical application. A patient receives a blood transfusion through a needle of radius 0.2 millimeters and a length of that needle of 2 centimeters. The density of blood is 1,050 kilograms per meter cubed. And the bottle supplying the blood, so this is my blood packet connected by a tube to the person that has the needle in their arm, and that blood's going to go into them. So the bottle supplying the blood is 0.5 meters above the patient's arm. What is the flow rate, or what is the rate of flow through the needle if the viscosity of blood, which I'm going to represent by the Greek letter eta here, the viscosity of the blood is 2.7 times 10 to the minus 3 Newton seconds over meter squared. That's just our unit for viscosity. Okay, so what is the rate of the flow? So we're looking for Q. That's what we're using for our flow rate. Volume per time. So it'll be a meter cubed per time. Meter cubed per second is the unit that we're going to be looking for. Okay, so in order to solve this problem, well, we can use the equation that we just saw with that was showing us how to find the flow rate in a viscous fluid. And that flow rate is going to equal the difference in pressure. That difference in pressure is supplying the flow or causing the flow of our blood, divided by this quantity R here, where R here is not the radius of our needle or tube. It is our resistance to laminar flow inside a tube. So inside that needle, be the resistance of laminar flow inside that needle. Okay, so that's what we're looking for. We've already seen that this equation, I'll write it over here, for this resistance R is equal to 8 times our viscosity times the length of the tube divided by pi r to the fourth, where this little r, that is the radius of, that'll be, in this case, the radius of our needle, and L will be the length of our needle that's inserted into our person's arm. Okay, so I see over here that R is on the bottom of this equation. So this is the same thing as P2 minus P1 times 1 over R. Okay, that whole thing. So whenever you divide by a number like this, we're dividing by a fraction. R is represented by a fraction. When you divide by a fraction, you multiply by the reciprocal. Okay, so the reciprocal is the inverse of this. So 1 over R is equal to the inverse of this expression. So it's equal to pi r to the fourth all over 8 viscosity length of my needle. So here I can rewrite this as P2 minus P1 times 1 over R, we just saw was pi r to the 4 over 8 eta L. This difference in pressure is what's causing the flow of the blood through the needle in the person's arm. Okay, and so that difference in pressure, the difference in pressure between here and here, that difference in pressure is only going to come from the pressure from the height of the column of blood here. And that column of blood is the blood essentially in this tube that's connecting our container of blood to the person. And we saw previously that the pressure coming from a column of fluid above you, that pressure is just the density of the material times gravity times the height of that material. So this difference in pressure that's supplying the flow through the needle is just going to be equal to the density of blood times gravity times the vertical height that this bag is above the person's arms. We'll call that rho GH here. So I'm going to replace P2 minus P1 with rho, which is now the density of blood, times G times H, the height that the bag of blood is above the person's arm, times pi times the radius of the needle to the power of 4 divided by 8 viscosity of the blood times the length of the needle. Okay, so all right, this time I will plug in all the quantities. We've got density of blood is 1050 kilogram per meter cubed times 9.8 meters per second squared times the height that the bag is above the arm, 0.5 meters, times pi times the radius of our needle, 0.2 millimeters. That's the same thing as 0.2 times 10 to the minus 3 meters. 1 millimeter is 10 to the minus 3 meters. So this is 2 times 10, 0.2 times 10 to the minus 3 meters, all to the power of 4. And then we divide this whole thing by 8 times the viscosity of our blood, 2.7 times 10 to the minus 3 Newton second over meter squared times the length of our needle. They gave it to us in centimeters. 2 centimeters is 0.02 meters. Okay, plug all that in and we find that the rate of the flow of blood through the needle in the person's arm is equal to 6 times 10 to the minus 8 meters cubed per second. It seems small, but it's enough to force that blood just through gravity into the person.
So let's take our non-ideal fluid a little bit further and talk about what happens when you have fluids that are turbulent. At high velocities, fluid flows change from laminar to turbulent flows. And the turbulent flow is characterized by irregular motion of the fluid, not these nice, beautiful streamlines, but things start spinning around. The Reynolds number is an indicator of whether the fluid flow in a tube will be turbulent or laminar. The laminar means that all the fluid layers are moving on top of the other, but turbulent means that you've got some spinning of the fluid, and then you create these little swirling eddies or vortices. So here we have an example of fluid moving through a tube, and on the left end here, we've got a very laminar flow, and then the cross-section changes to a point where inside the new cross-section, the fluid now becomes turbulent. The difference between are you turbulent or are you laminar has to do with the Reynolds number. And the Reynolds number is classified, at least for fluid moving through a tube, the Reynolds number is given as 2 times the density of the fluid times the speed of the fluid times the radius of the tube divided by the viscosity. If you have a Reynolds number greater than 3,000, that indicates a turbulent flow. If you have a Reynolds number of less than 2,000, that indicates a laminar flow. Now somewhere in between there, you've got properties a little bit of both. For this engagement check, I'm going to ask you to rank the fluids flowing through a pipe in order of most turbulent to the least turbulent. So you're going to use your equation for the Reynolds number in order to decide how turbulent are these flow patterns inside the tube. And so you're given 4 scenarios. You're given the density of those fluids, the speed at which those fluids are moving through the tube. You've got the radius of the pipe or the tube, and the viscosity. And you're going to use those quantities in order to rank these scenarios from most turbulent to least turbulent. Before, we were only thinking about turbulence inside a tube. Now let's think about turbulence that you can form around an object that's moving through a fluid. Okay, so Objects in viscous fluids will experience turbulent wakes behind them. And this turbulence is classified by another formulation of the Reynolds number. So there are different scenarios you can have different Reynolds numbers. In this case, this Reynolds number, which still tells you how turbulent the system is given as the density of the fluid times the speed of that object moving through the fluid times the length, the characteristic length of that object that's moving through the fluid divided by the viscosity of the fluid. So this Reynolds number is different than the Reynolds number we saw for fluid moving through a pipe. And you can have something that is equivalent to a drag force, except for moving through a viscous fluid. And so this sphere, as it's moving through the fluid, is going to experience essentially a fluid drag force. And that fluid force is given as 6 times pi times r, where r is the radius of a sphere, eta is the viscosity of the fluid, and v here is the speed at which that object is moving through the viscous fluid. So a small sphere of radius r moving slowly with a speed v in a viscous fluid experiences a drag force. Similar to the drag force that objects experience when they're falling through the air, this is a drag force for objects that objects experience whenever they're falling through a much more viscous fluid than air is. And we're going to apply this later eventually to another problem. This drag force operates in exactly the same way as the drag force we saw whenever we were talking about motion of an object falling vertically through the air. That drag force always opposes your direction of motion. And so here in these figures, we have our sphere, and the sphere is moving through a fluid, okay? And the faster the sphere goes, or the faster the fluid moves around it, the faster it's really the relative speed between the object and the fluid around it. The greater that relative speed between the motion of the object and the motion of the fluid, the more turbulence you can build around that object.